questions, anyone? Yes.
So I asked you that question in the morning, like you have to clean up in the try catch. But what happens when I put the cleaning up statement? Basically, I set the global variable to empty at my last statement, and
No, you don't want to set it to empty. You want to set it to the tail of itself, because there may be other stuff on it.
that I do when I am matching in my throw functions. When I'm actually finding a matching catch, I pop it off. I don't.
But even if,
I do set the global variable to the rest of the list.
but you also need to do that when you simply exit the catch clause.
So you're saying after handling, after I
Well, even if it was never handled, if you exit a catch clause,
right.
then whatever it is that it was willing to catch, you need to pop up.
So what happens if I do that? At my last statement, I'm losing the value of my answer.
Well, yeah.
But then after doing that, if that variable doesn't get assigned, it just prints whatever you initialized it.
So you do have to do it.
No, you will come there. You just see you put it in semi-continuous.
Okay, you're going to have to just put some question on. I don't think this is going to work in class. Other questions? Okay. Then, yeah.
Yeah, so same question, what are you assigning it for?
I'm going to think about whether I'm going to assign projects or whether I'm going to drop them.
Can we, instead of the midterm, can we replace it with projects or something?
No, there is a requirement to have these midterms, so we're going to do that. And actually, we need to do it next Tuesday because I'm out of town, and you might as well do it then. I just need to find a problem. So next Tuesday, I'm out of town. I'm at yet another conference, and so we'll just use that for catching up with the midterm.
So we're doing a second midterm next week?
It's going to be it's going to be the first midterm. I'm going to trash the results of the first midterm. Or let me put it like this: you'll get the better of the two. So
the exact same questions are going to come up? I'm confused. I'm really sorry. I'm confused.
No, it will not be the exact same questions.
I wish they were.
Don't wish for what you might be getting. I might just give the same questions and then make it closed book, and then what? No, that won't be the exact same question. I'll just have to cook up some other set of questions. What can I do? It's not my idea of a good time either, but I will come up with a new set of hopefully easier questions.
Will it be over the same material or some more
They'll be over whatever it is that has been covered until next Tuesday. I mean, so today and Thursday is fair game.
Can you get some extra time? I think time is a big constraint for us.
I guess that if people can make it longer, but then everyone would have to be able to make it longer. If you want to canvass the class and see that everyone wants to stay 15, 30 minutes longer or whatever, I will find a proctor to proctor for that. But if people need to go back to work or something, I mean, anyone who does not want to do that can send me a private email saying I didn't want to speak up in class, but I just can't. And if anyone does that, then
we will not have.
Then you will have the regular custom. I mean,
another class that comes in here.
Yeah. So if you can arrange something else.
You would come in. Well, there's a limit of what we can arrange. It can be in this room. You can, I could clear out the previous class. In fact, the previous class, since I'm not teaching and I have the room before that, I was going to have them do a lap, but I can tell them to be out here by 1. So if people wanted to say have it from 1 to 2:45 as opposed to 1:30, If everyone is okay with that, you know, I'm fine with it.
You anyway don't check the time, right? I mean,
What's that?
you anyway don't check the time.
Well, if someone needs to, I mean, if, what do you mean I don't check the time?
I mean,
I
last
get-
time, last time I turned, I committed like 5 minutes later. I mean,
Yeah, you don't think I didn't notice?
Yeah.
But I
You're
said-
supposed to say that.
But I figured since it was so pathetic anyway, what I was gonna get excited about those 5 minutes.
so like,
So, I mean, I know perfectly well when it's checked in, right?
yeah.
So I'm not concerned about the 5 minutes. So if you guys want an extra half hour, that's easy enough to arrange. You guys just need to let me know. If you have another class and you can't, then it's unfair, then I can't do it.
And could you do us a small favor in that? According to you, how much capable you think we are right now? Could you just put in a time limit on the question, as in we should be spending this?
Oh,
much
that's a good
time?
idea.
So we have an idea as to, we don't get stuck on one question at the same time, you know?
Sure.
Something like
Sure,
that.
I can do that. Yeah.
So,
Going
yeah.
to have another midterm? That because
Hello?
I just missed it. And
We're just talking about that we're having another midterm next Tuesday.
next Tuesday?
Yes.
Welcome to the real world.
And it's going to cover till continuations 3.
Or 4 if we get that far.
Okay, and on the green sheet, they specify that we will be having projects, and I prefer having projects, so.
You can certainly have the projects in addition to the midterm,
Yeah, in
but we
addition
will
to
have
that.
all right, so if you feel that I promise projects, therefore you must have projects, I will give projects. Yeah.
That's great.
Yeah, with any of these things, it only takes one person then.
Could you give us some extra credit so that we
No,
can at least-
it doesn't say on the midterm that I should, you know, on the green sheet that I should give extra credit for anything. In fact, it says the exact opposite. Right? So I think I'm already bending over backwards by giving a second exam.
So second exam is replacement of the
Yes,
first?
yes.
Completely.
What I'm saying is, I will count the higher of the two.
We see it more as a threat right now. Out of the two, that means, I hope the exam's not as tough as it was.
Could someone like, put some caffeine into that person? It was meant to be as a joke.
That's kind of afraid.
All right. And, any other questions about this?
No Rails or web servers.
Yeah, Rails, we're not doing that.
Yeah, that's fair. I mean, it says no Rails. Yeah,
Yeah, that's-
it takes too long.
No continuation, yes, but-
Oh, there'll be something with continuation. But, oh, not the web server. Not the web. Nothing with web servers. Yes, it takes too long.
One more,
Yeah.
this is a small request, could you give us some practice questions, over the weekend or some?
Put it on Piazza.
Yeah, so I guess we'll just be worked on as to mentally prepared as what we're doing. Because we've seen one exam, I understand that, but. some practice
Put a request on
questions-
Piazza. I will have
Yeah.
forgotten by the time I get home. So if
Yeah,
it's there, I'll
that'd be helpful.
Yeah. Other questions? All right, moving on, back to eliminating tail calls. So, so we're having back here. Oh, let me turn the lights on. We're having back here the factorial with the usual recursive thing where it's not in tail position. So over here it's buried somewhere inside, inside the multiplication. So it's not a tail recursive function. And now we want to rewrite it in tail recursion. So watch closely, this won't hurt a bit. So now I'm going to take my original factorial, which took one parameter, namely the number, and change it into a function that I call fact/k, which is the CPS rewrite. And so the slash k is just a name. And now it has two parameters. The original one that I had before, and then this parameter k. And so the idea is that k is the future of the computation, what should happen later. So over here we're saying if n is at most 1, then I'm just going to be using k to deliver the answer. So k is kind of the rest of the computation, and you've seen this many times before, that when you just call the continuation with something, then it pops out somewhere where hopefully the result is expected, and now someone is going to get the happy news that the answer is 1. So in general, when you find something here that doesn't, that is just a simple value, then we're going to pass it on to k. And now we have the harder case here, where we're now going to be rewriting this n-1 part here. And then we're going to say what it should do after it has subtracted 1 from n. And what we're saying what it then should do is that it should take, so that now the continuation is to whatever it is that came in from there, it should be multiplied with n, and then one should keep going with that. So let's just try it out with this example here. So first of all, notice that the function that I have here is tail recursive, because fact k calls itself in a tail recursive position. And now let's see a little bit more how it works. So here we're calling fact k, this is our first parameter 3, and on the outside we're calling it with the identity function. That's we have to give it some kind of a function here because we've promised a function parameter, and you'll see why it works. So lambda xx is the identity function. So it says, what are we supposed to do? N is not 1, so we're calling it recursively, and now we're calling it with the function that multiplies something with 3, because that's what this happens to be. And let's say n is 3, because we're calling it with 3, and r was just this function here. So all we did is we substituted for n to 3. So now we're calling it one more step. And now we need to be a little bit, also notice this k here, because I plugged in the identity function. The identity function applied to times Rn is times Rn again. So now we're calling it one step further. So the 2 becomes this 1 here. Now this lambda here, I'm calling it R2 because otherwise the R's are hard to decipher. So what does R2 get? It gets, we have to plug in the correct k. Well, in this case, the k is the function over here. It's the function that multiplies with 3. So we now take the 3 multiplying function and apply it to this times Rn. Here's the 3 multiplying function, and here is the times Rn, except R has been renamed to R2, and n is 2. So we're now calling it with the function that multiplies with 2 and 3. And finally, because it's 1, then we can call this function here with the value 1. We're evaluating k of 1 here. So if we're calling this function here, where R2 is 1, then it multiplies 1 with 2, and then finally with 3. So in a weird way, what's been happening here is that in the second argument, in this argument k, as the recursion unfolds, we're keeping track of the steps that still need to be done. And we're collecting them in this function which eats another function. And so if you look at, again, the problem with the absence of tail recursion was that the fact was not the last thing to be done, but there was still this pesky multiplication with something that had to be done after the fact happened. So in the first iteration, this thing that was left to be done was to multiply with 2, and then afterwards the thing that was to be done was to multiply with 3. And here you see how this nesting of these functions accomplishes keeping track of them. So that's how you can use continuations for recursion avoidance. So the version that I've written here is a tail recursive version of the factorial, and it's not really any more complex than the regular version. It looks just the same except for these funny lambdas here. And the lambdas, as they build up, they look a little messy, but it's not really, there's not really anything terrible going on. So in this case, the transformation from this form here to this form here is actually beneficial. So it means that we don't have to consume large amounts of stack space. This thing can run as a loop. And yes, as this loop proceeds, we're building up some crazier and crazier function, and eventually that function gets executed on the humble value 1, and then that function unfolds. So you might say, isn't it expensive to build this function? Wouldn't it be cheaper to have some stack space? But the thing is, you usually have a lot more heap space than stack space, so that's considered a beneficial trade-off. So now the question is, how can we always do this? So, so the general idea is that when you transform any old functions, think of factorial into CPS, then you add an extra parameter, and that's this function k. And k says what should happen with when f is done. So notice also that the function, the fact k function here, it doesn't really return in any meaningful way. There's no return value anymore. So just think about for a minute of a world where functions don't return. You call a function, and that was it. It's just a black hole. But the way you call it is you give it an extra argument. You give it a callback. And you say, hey, when you're done, use that function and invoke it. And then that's how you're going to get called back. Now that's not such a weird idea, because that happens all the time when you do asynchronous processing. Whenever you do some wait and forget style asynchronous processing, you have to somehow get notified that the answer is available. And so it's common to just give some kind of a function, say call this function when you're done. So that's basically here what we're doing is we're telling fact, go on your merry way. I know you'll never return, but when the answer is available, you don't have to come back to me. You just tell this function, and that's the step over here where we're saying when the final answer is available, call it through this function. So and so every time that we call something, we say, when you're done, use this function. Yes?
So in such functions, the control never gets returned back to the calling program?
Well, it gets returned, but it gets returned through this continuation. So yes, I mean, we'll get the answer back. Yeah?
I'm a bit unclear on the use of k in the continuation.
And this slide or this slide?
The second, previous, yeah, this one.
Yeah?
The second one. So k. So the function is called again, right? So
Yeah.
it terminates when the value of the number that is for which we are trying to find the factorial is 1 or less than 1.
Yes.
So what is exactly the use of k in that? Is it signifying?
K is what we want fact flash k to do when it's done.
So it stores the result, or any given. Sorry.
The first when the answer is 1, then it feeds 1 to k. And k gets built up to be more and more complicated, because the first time that you call factorial, then it wants to call itself again, and then the pesky business, it didn't have a chance to multiply the result with n. So it says, by the way, when in the next step, be sure to do that after you're done. So when fact3 gets called with the instructions, when you're done, just run the identity function. So it calls fact2. And now the instructions are a little bit more complicated. The instructions are, when you, fact2, are done, make sure to multiply the result with 3, and then call the identity function. Fact2 calls fact1, and now the instructions are, remember, you need to multiply with 2 and with 3, and call the identity function.
But there will be still, at least for this case, there will be 3 frames in your...
No, there will only be 1 frame because this thing is a jump.
So actually k is like it is telling the function that you need to do these previous steps over there?
Well, there's subsequent steps.
Subsequent
There's
steps.
steps to be done afterwards.
Yeah, right, after doing this, you multiply with 3.
Yeah. Normally, when you call a recursive function, you call a recursive function and you do a little bit more work. But in continuation passing style, you call the recursive function and you tell it to do a little bit of more work afterwards. So it's like, normally if I had, like, in the good old days when I had an office assistant, I could say, you know, do all of this, gather all of this information and bring it back to me. But of course, it's so much better to say, gather all of this information, and when you're done with it, you do all of this other stuff with it too. And so that's, any time that you call yourself in continuation passing style, that's the last thing you do. And you say, do your thing, and when you're done with it, subject it to this transformation. Yeah?
It's jump because internally this is mapped to a callback.
Yeah, it's jump because this is in a tail position. It can be a jump. So anytime that you have a recursive function where the recursive function call is in a tail position, it automatically turns it into a go. And so it's a CPS function, because it just calls itself with simpler values. That's the whole point, that it is automatically a tail call. Something is not a tail call if you do other things after the function returns. Well, a CPS function will never return because it just tells someone else what to do afterwards. So it never has anything else to do afterwards.
When we are calling this function in the continuation, so we call.
Well, be careful. There is no actual continuation here, right? This is continuation passing style.
Yeah, yes. So when we're calling this function, as in the function we define here, so how do you say, I want to find factorial of 4.
Yes?
So I just pass fact/k of 4.
Yes?
And the second value would be? Do we need to write that when we're calling?
Yes, because it needs a function.
Okay.
It needs a function. This thing doesn't have default arguments or any such sissy syntax. So we have to keep it a thing to prime the function.
So k is actually the function that's being run.
Yes.
Right.
Yeah.
So what?
It's tail recursive. We've eliminated filling up the step.
I mean, it's returning a factorial itself. So how do you use fact k other than just getting factorial out of that?
I mean, fact k is computes factorial just like fact did, in which, as we know, is the entire purpose of most computing power in the universe. No, factorial is just an example to show the transformation. No one cares about factorial. But factorial by itself was not tail recursive. It consumes stack space that's proportional to n. We have now rewritten it in a way that it no longer consumes stack space.
Is this a single line of code?
Okay.
And we have done this in a way that is completely generalizable. Nothing in this transformation used anything specific about factorial. As you'll see in the next couple of slides, you can do the exact same transformation in complete generality. Factorial is just an example because we understand.
Okay.
So let's do this formally. So what we want to be able to do is write a function that's called CPS that takes any old lambda expression, or I should say, any old lambda expression, and transforms it into its CPS stuff. So, and there's 3 rules to do that someone cooked up that make this work, and they don't look so pretty, but they work. So CPS on a primitive expression, that means you rewrite it like this. So primitive one is something that doesn't contain things that we need to simplify. Multiplying, addition, variables, lookup and stuff. And so in this case, we transform it to lambda k and then apply k to the primitive expression. We just do this, trust me. When we have a function application, then we transform it into the following mumbo jumbo. And what it says in plain English is we transform the function, we transform the thing that it works on. So here we're assuming that we only have a single argument, and by using currying, you can always reduce things to a single argument. And so it says we're transforming the function, we're transforming the argument, and then when they're both ready, then we apply them and give them k as the continuation. And when we have a lambda abstraction, then we rewrite it in this way that I don't even want to. We'll see it in action. So these three rules are enough to be able to compute the CPS transform of any lambda expression, because that's really all the kinds of expressions that you'll ever have. You have function application, you have lambdas, and as you know from your evaluator from the homework 3 thing, there isn't really much else. You can evaluate anything that has, what are we doing? Some primitives, letrec, function application, anything else? That's it, right? Lambda, letrec, function application. Those three things together, plus a few primitives, are all the computational power in the world. Which by itself, if you think about it, is actually kind of stunning. But so if you know how to transform these, you can transform everything. So, do I want to do this? Yes. So let's go through an example here, just to see how these rules work. So here we are having a list consisting of the expression square and 3, and now I want to compute the CPS of that, and the CPS eats some functions. I'm giving it the identity function. So this thing I, whenever I use I on these slides, it means the function lambda xx. All that says. All right, so now it's a function application, right? It's one thing applied to another. So I need to use the function application rule from the previous slide. Now it would be good if we could remember them all together. You haven't, but do you think I remember it? So here with the function application. Okay, lambda k, CPS function. Okay. See if I remember this. Lambda k, CPS of the function, lambda s, CPS of the argument, and then the argument lambda phi, and I counted all those parentheses I know. So I'm just using this transformation. Now, here I have a lambda, and it eats an I. So whenever you have something of the form lambda, and then something, and then some expression that involves A in some way, and then you have it eat some expression B, what that means is you drop this stuff, you substitute B's whenever you find an A in it. That's what lambda application means.
So the I
So now what I can do is I can drop the lambda k. Wherever there was a k, I can put an I. And I'm sure that's the rewrite that I did here. That is lambda application, if I just want to figure it out. So what's my next step? Over here, I'm taking CPS squared. It's a primitive, so I'm rewriting it as this thing. All right, now I can do lambda application again. So over here, I have lambda k, and then it eats some big fat argument. So what I get to do is this thing is k, and so I put it in front of square. So I took the thing back here, put it in front of square. So now I need to compute, and I guess I have another lambda application that I can simplify. I have a lambda f here, so I can take this, I drop the lambda f, I find my f's in here, there's only one, I put square in there, and I have this simplification. So now what is CPS of 3? That is lambda k3, because that's how CPS works on a primitive. And now I do it again. So I take this thing here for k and put it in front of the 3. And now I do it one more time. I have an A here, that's the A here, so the 3 becomes A, and now it's square 3. And then it computes square root of 3 followed by R. Yeah?
Could we do this a bit slowly? After the first I kind of got lost over there.
Which one?
After that, we replaced the k with I, right? And we removed the lambda k function at the start. Yeah, the first line. The second.
Okay, you want to find out, do you know how to go from this line to this line?
Yes, I know.
Do you know how to go to this line?
Over there, you remove the square function.
So what step was involved here?
So we're removing the square function. and-
Not yet. To go from, if I may number these lines, 1, 2, 3, 4,
Transform
5,
CPS
6,
square
7, 8.
to,
So how do we go from line 2 to line 3?
CPS transformation.
Yeah, that's the definition of what CPS of square is.
Okay, so we're.
Square is a primitive, and so the definition of a CPS of a primitive is it's lambda k, k of that primitive.
Okay.
I've used that step twice, once to go from here to here, and once to go from here to here.
So after 3, so from 3 to 4.
That was lambda application. So over here, I have a lambda k, k squared,
Okay.
and that consumes this big fat expression on the right.
Right.
So that big fat expression becomes k, which means it gets put before square. Here's the exact same big fat expression.
And square
here's
is on
square.
our side. Okay.
Okay?
And the same lambda function.
Yes, and so every step here is either using one of the definitions or lambda application.
so is this a, is there a library function which can?
You'll be able to use that function in the lab, yes.
So in the earlier slide, you said the CPS takes a primitive expression.
Well, it takes one of 3 expressions. It's defined for 3 expression types: primitives, lambdas, and function application.
So when we are just saying CPS of square, that comes under primitive expression,
Yeah, assuming the square is primitive, yes.
but that doesn't take any arguments.
It does take, because when you look at what happens, CPS is the result of CPS is always something that takes a function. So in the 3 cases, it's a lambda k. So over here it's a lambda k, lambda k, and lambda k. So CPS takes an expression and turns it into something that eats some function.
So my question is that when we said that square was a primitive expression,
Yes.
assuming that square was a primitive,
Yeah.
we are not passing any argument to square. So as it is, when you write the name of a primitive, it is considered as an expression.
What's that? Okay, I think I know what you mean. So I should show you what square looks like.
It's a variable lookup, right?
No. So what square is supposed to look like, what we would like square to look at like, is we want square to be lambda x times x, right?
Correct. So that square function takes a argument.
Right, but, okay, this function here, now have a look at this square function here, right? This function has a fatal flaw. What's the fatal flaw of this function? In the world of CPS.
It's not tail
Well, it's not even recursive.
No.
But that's fine.
Uh,
No, it's something much more horrible.
X is
Nothing. I don't see anything wrong with
it
that.
returns something?
It returns a value! Right? I mean, if that doesn't make you cry. Here you have a function that returns a value. You're not supposed to return a value in the world of CPS. What are you supposed to do?
Call k and.
You're supposed to give it to some other function. right? So we need to actually have even the most basic building blocks rewritten in continuation passing style. And so I have to then say, fine, it takes two arguments. Like that. Okay, now the square thing has its regular argument plus the thing to which it hands off the answer. And it computes its thing and hands it off to K. End of story.
So K is a function and X is the variable for it. Just
Yeah.
like the factorial one.
Yeah.
Yeah, N and K. Right?
Yeah. So now that's almost the right story. Now if you carefully look here, you see that instead of having lambda xk, I have a lambda x lambda k.
Yeah.
Why?
Because even for argument, you got to.
The reason is that it makes the
Recursion kind of?
no. It makes the calculus simpler if in this step here, I only had a single argument. Notice here I only had fun and arc, and I only had a single argument. Because if you write this thing down with an arbitrary number of arguments, it gets very messy. But if you do it with one argument, I can fit it on a single slide, and you can kind of rock your way through it. And you have learned many moons ago how to take a function with n arguments and write it as a function of functions of functions by doing currying. So this thing is simply what you see over here is the curried version of what I have before. And so as a matter of, in this game here, we're always going to rewrite our functions as being curried, just so that we don't have to deal with more than one argument at a time. And yes, I do not want to understand exactly what this means. Given an x, it returns a function that when
My
Yeah.
question is still not answered. So when in the second
Yes.
equal to statement you said CPS of square.
Which definition is applied there?
Yeah, so the definition that's applied there is the third one, which is CPS lambda x and body, correct? It's not
no. CPS of square, we assume square is a primitive.
But square takes an argument and
No. When a primitive is something that in its inside does not have a recursive call. That only has basic building blocks. So when I say primitive, I don't mean like an atom. So it simply means that something whose structure does not involve any recursion. So it's all made up out of basic functions and just nothing difficult going on. When you do this later, there'll of course be a homework assignment with this. There'll be an exact definition of what a primitive is. So there's a couple of limitations that, in theory, this is great. In practice, as you'll see in the lab, it generates lots of lambdas. It's tedious that it's only defined for single variable functions and that you have to do the currying. And it's also tedious that you need to have CPS versions of absolutely everything. So we would have to have CPS of empty and add and if then else. So even if then else. And here, just for fun, written down the if then else definition for, and it just looks so messy that you don't really want to deal with it. So there is a way of doing a refined algorithm, but I think in the interest of let's first go into the lab before we do this one. So because we're doing the basic one in this lab, and then we'll do the other one next time. So step one in the lab, use the basic transform, and you can do that. And you can do step 3. And I don't think we'll get to step 4, but I think we could even do step 3 with what we've done before. So we will need these 2 slides, the refined slides, when we go into the next homeworks, but let's skip them for now. All right, let's get going with this lab and see.